Moving on now to some of our AP style questions for this homework assignment. So we have our classic experiment conceptual question about the rock and the feather. And so if a rock and a feather are dropped at the same time near the surface of Earth, which one lands first? In the absence of air resistance, they would accelerate downwards and land at the same time, but on Earth we do have air resistance. So why will the rock land before the feather? The first one, the rock does have more mass. That is most likely true unless it's a really heavy feather, but that does not mean that gravity pulls it more. So question A, or response A, is going to be out. Gravity pulls both objects down at the same rate. The rock lands before because air resistance had a bigger impact on the feather. That one is absolutely true, but let's double check the other two. The rock lands before because the rock starts falling immediately and the feather does not start falling immediately. That is not true. They both start falling immediately due to gravity. And then the last one, the rock will not land before the feather. They will land at the same time. Well, if we account for air resistance, then that is not the case. In a vacuum, though, that would be true. All right, moving on here to our next one. An object is thrown straight up in the air and caught at the same height from which it was thrown. We're going to ignore air resistance. We want to know what will be true for the object. So first one, our velocity is 0 at the peak. That is absolutely true. This is one of the ones, though, where we have to select more than one correct answer. So I'm just going to put a check next to that one. Acceleration of the object at the peak is 0. We know that it's 9.8 no matter what. The object will take less time to fall than to rise because velocity and acceleration are the same direction. That is also not true. It's a symmetrical launch. And then D, the time it takes the object to rise equals the time it takes to fall. So that one is also true. So the answers are A and D. Both of those statements are correct. Moving on to 8 here, it says that in the absence of air friction, objects drop near the surface accelerate at a constant rate, 9.8 meters per second squared. So what does that actually mean? This first one, the speed increases about 9.8 during each second. That one is absolutely true, and that does end up happening to be our right answer, but let's work through the other ones. The speed as the object falls is 9.8 meters per second. That is not necessarily true, but there may be a point in time when that happens. The object falls 9.8 meters during each second. That one's also not true. That would imply that the velocity was 9.8, not the acceleration. The object falls 9.8 meters during the first second only. That's the same idea. 9.8 is the acceleration, not the velocity. Completely separate topics. And the rate of change of displacement with respect to time for an object. That really is another way of saying velocity. And once again, the velocity is not necessarily 9.8. That is the acceleration due to gravity, but will not be the velocity for an object in free fall. All right, for this problem here, we have a red-bearded tuba player running down the sidelines of a football field at a constant velocity of v. Immediately after the tuba player passes a detective whose name is Holmes, who's initially at rest, that detective begins chasing the tuba player. The detective accelerates at a rate of a, and we want to know how much time will pass before he catches the tuba player. So I'm going to set up two things here. I'm going to have my red-bearded tuba player, and for that I'm going to be thinking about my displacement, my initial velocity, my final velocity, my acceleration, and my time. And so for the red-bearded tuba player, we know it's a constant velocity of v, so that means both my initial velocity and my final velocity are just v, and my acceleration is 0. I'm also going to set something up for my detective here. Exact same things that we're thinking about. Our displacement, our initial velocity, final velocity, acceleration, and time here. Okay, and so for the detective, we know we're starting from rest. We know we're accelerating at a rate of a. We don't know anything else for sure, but we do have two important connections here. The first is that both the detective and the tuba player will travel the same distance, so I can say that this is x, and I can say that this is also x. We know that the detective starts running as soon as the tuba player passes, and we know that the detective eventually catches the tuba player, and therefore they must travel the same distance. or have the same displacement over that period of time. And we also know that the times are the same, and I'm just going to call both of those times t. All right, and so that's a key piece to this problem, is recognizing those two connections, that these are the same and that these are also the same. Now that we have both of those, we're going to set up an equation for each. Keep in mind that when we have zero acceleration, like we do here for the red-bearded tuba player, there's only one useful equation. Well, really two useful equations, but it's got to be one of the delta x equations. So for the tuba player, I'm going to say delta x equals VIT plus 1/2 AT squared. The acceleration goes away because it's 0. So for the red-bearded tuba player, I'm just going to say x equals v times t. And there we have that. And for the detective, I'm going to set up an equation as well. We don't know the final velocity at all for the detective, so I'm going to use the equation that doesn't include final velocity, which is the exact same equation here. We do have an acceleration though, just no initial velocity, so that term goes away, and we can say x is going to be 1/2 AT squared. We now just need to combine these two equations. I think the easiest thing is, since they're both equal to x here, we can just set them equal to each other. So v times t is equal to 1/2 AT squared. The times, one of the t's will divide out, and what we're left with then is v equals 1/2 AT, and if we solve for that time, we get 2v over a is equal to t. Be aware we did drop a solution when we did that. Whenever you divide both sides by the same thing, you do need to be aware if you lost any solutions, and we did right here, but there is an easy way to find that solution. So what value could we plug in for t here that would also work on both sides? And the answer is 0. All right, and that makes sense. Okay, this t equals 0. That would work as a possible solution because at 0 seconds, the displacements are the same. Right? Neither person has really traveled any distance at 0 seconds, and so it makes sense that that's a solution. However, that's typically what we refer to as the trivial solution. That's not the one we wanted. We knew they were at the same location at 0 seconds. What we wanted was that other time when they're at the same location, and that's this time here, 2v divided by a. All right, let's move on to part B here. We're going to be using the same setup that we had over here for part A, but now what we're doing is we're trying to find how far we go, and so we're really just looking for delta x. So I'm going to take an equation that I used before, and it's going to be the equation for the detective, that x is just equal to v multiplied by t, and all I'm going to do is I'm going to substitute in the time that I solved for before, which was that t is 2v over a. So I can say x is equal to v times 2v over a, which simplifies to x is equal to 2v squared divided by a. And so that would end up being how far we go. We knew our time, and so all we need to do is just sub in that time and use that to figure out what our distance would be at that point in time. All right, for the part C, we want to go ahead and draw our position versus time and our velocity versus time graphs for each of these situations. So for the tuba player is traveling at a constant velocity of v, which means the position versus time graph is just going to be a straight line with a positive slope, something like that. Our velocity versus time graph showing a constant motion is going to end up being a horizontal line somewhere along the x-axis, so something like that. For the detective, our position versus time graph, we're going to be showing speeding up, and we eventually are going to intersect this line again. We'll talk about that a little bit for part D, but speeding up, that would look something like this. All right, positive slope, but getting slopier or concave up, indicating that the detective, the speed of the detective is increasing. And then for the velocity versus time graph, it will not be a horizontal line. It will be a line with a positive slope, something like that. All right, for question D here, we have 3 questions about the graphs. The first is, was the intersection mean on the position versus time graph right here? So if we think about that, when they intersect, it means that they have the same y value, in this case position, at the same time. And so since this is a position versus time graph, that ultimately means that they are at the same location. Okay, that's what that intersection point is going to mean. On the position versus time graph, they're at the same location. On our velocity versus time graph, the basic idea is the same. It means that the y value is the same at that point. And so what does it mean on the velocity versus time graph? Well, it means they're at that same velocity. So this intersection point here is indicative of when the tuba player and the detective have the same velocity. And lastly, do they happen at the same point in time? You can see from the graphs probably not, but that could just be how I drew them. The answer though is no, they don't. This point is going to occur first. Okay, the detective will catch up to the speed of the tuba player, will reach the same speed of the tuba player before the detective actually reaches the same position. Okay, and we talked about that a little bit before, but you got to keep in mind that the detective ultimately needs to be running faster than the tuba player in order to catch up. All right, so this point over here, okay, is when that happens. And another way of looking at it is we know that the area of this triangle would have to be the same as the area of this rectangle at that point when they catch up, and clearly that's not going to happen at this point here. Okay, those areas have to be the same because their displacements have to be the same. So the intersection point for the position happens later. So the first one to happen is the intersection point for the velocity when the detective reaches the speed that the tuba player is running at. All right, for this problem here, we have a person parachuting off of a building. We're told that for the first half, the person is accelerating at, in free fall. So the acceleration would be negative g, just going down. And then about halfway down the building, or exactly halfway down the building, they pull their parachute and their velocity becomes constant, which means that their acceleration is 0. Now this technically is unrealistic. In reality, they'd slow down a little bit, but it simplifies the problem. So the first question we're asked is, will the person spend more time in the first half of the building, the second half of the building, or will those two times be equal? All right. And what you really have to keep in mind here is that for the first half, the person is in free fall speeding up. After that point, they maintain that constant speed. And so the first half of the building will take more time because overall, or on average, the person is traveling slower at that point in time, right? They're speeding up to some maximum speed that occurs right here at that halfway point, and for the rest of the time, they're traveling at that maximum speed. So for the entire first half, they're traveling slower than the constant speed that they maintain for the entire second half, and therefore it will take more time to cover the first half than it does to cover the second half. All right, for part B here, we're asked to find the velocity of the person when they open their parachute after falling that height of h over 2. So I'm going to go ahead and set up my equation here. So I'm going to say displacement is negative h over 2. My initial velocity here is going to be 0, and my acceleration is just going to be negative g. The reason why I made this displacement negative is because the object is losing height, so we want to indicate that with that sign. So we have three things here. We're going to solve for that final velocity, and I'm going to use that VF squared equation. And so we are looking for VF squared. We know our initial is 0. Acceleration is negative g, and our displacement is negative h over 2. And that's where that sign really comes in handy, because now that ends up being positive, and we're not stuck taking the square root of a negative. We go ahead and solve for VF, and what we end up getting there is that VF is just going to be the square root of GH. However, since we took the square root of VF squared, we are going to be left with plus or minus here, and because we set down to be the negative direction, there should be a negative sign in front of that VF. All right, for our next question here, we're now going to find the time it takes to go that distance. And so we're going to use the same setup here that we have already, but now we're just going to be thinking about time. And so I'm going to use the VF equation. VF equals VI plus AT. I know my final velocity is this negative root GH, and that's equal to 0 minus GT. And so when I go ahead and solve for t, I divide by g, and what I'm left with is the square root of GH over G. That's one possible option for our time. We also, though, can really do the square root of gh over root g times root g. Then the g's cancel out, and you're left with the square root of h over g is equal to t. So you do have a few options here for possible answers. Either one really is fine. I wouldn't say one is in a simpler form than the other. They're both pretty clear. There are a few other ways of doing it. You certainly could have used the delta x equation or some other equation, but I just chose to use this equation. So whatever you use is perfectly fine, but those are two of the most common possible answers, two of the most common forms of the correct answer, I should say. All right, for the last one, we now want to find the time for that final half. And so we're going to set up a new equation because we're no longer dealing with the first half. And so for that final half, we know that our displacement, once again, is negative h over 2. Both our initial and final velocities are going to be this negative root gh. At this point, you could probably make everything positive if you wanted, but we'll stick with the negative that we've been doing, and our acceleration is 0. So we want to solve for this time. Since we have that case where there's 0 acceleration, we know we have to use one of those delta x equations. And so I'm going to say negative h over 2 is equal to my initial velocity, which is negative root gh multiplied by t. That second term all goes away because the acceleration is 0. And so I find that my time is going to be h over 2 divided by root gh. All right, and that, I guess, is kind of an acceptable form of the answer. Most likely we'd want to get rid of that double fraction, and so we could multiply top and bottom by 2 and say that the time is h over 2 root gh. So that's one possible option. The other thing we could do is on top we could say h is really root h times root h all over 2 root gh. And much like in the last one of those h's will divide out with the h on the bottom, and you're left with t is equal to root h over 2 root g. Moving on to our final question here. This is going to be a paragraph-like response style question, so we'll talk about that briefly in a little bit. But we have a situation where there's two people standing on top of a roof. Each of them has a rock. And they're going to throw the rocks, all right? One person throws rock A straight down with an initial velocity of v, so it's going in the negative direction initially. And the other throws the rock straight up with that same velocity. So the first thing we want to do is, on the graph, we want to draw the velocity versus time graph for both objects from time t equals 0 to the point when they hit the ground. So I'm going to go ahead and start with that. So first I'm going to draw rock A, which is starting with that negative velocity, and it is going to simply be speeding up as it falls. All right. Rock B is going to start up here with the positive velocity, and initially it's going to slow down, okay, to 0, all right, as it rises to its peak. And then it's going to begin speeding up in the negative direction. So continuing on down like that. Okay, something like that. One thing we should notice is both of these objects are accelerating down at 9.8 meters per second squared. Okay, so the slope of the two lines, and obviously it's not easy to get this perfect, but they should be relatively the same. Okay, in theory they are exactly the same, but obviously it's a little bit difficult to draw that. All right, so it should look something like that. The second part says, in a clear, coherent paragraph-length response, explain which rock will be moving faster when it hits the ground. Feel free to use this graph to provide some support. So we're going to talk a little bit about this question in general. With these types of questions, we want to first make a very strong statement, all right, just answering that question, and then we're going to provide evidence. And usually it's going to be in a very logical format where we state one thing, which leads to another thing, which leads to another thing, ultimately explaining our answer. So I'm going to start with stating what the correct answer is. And the correct answer is the rocks will hit the ground traveling at the same speed. And there are a few ways I can do this. So let's talk through the solution and then we'll write out an answer. So the one thing I can think about is, All right. If I just think about the path of the two rocks, all right, the one, rock A, is just going to go from here straight down, and so it's initially traveling at negative v at that spot. Rock B is going to go up to the peak and then go down, and it's initially traveling at v when it leaves the person's hand, but that means that when it returns to that same spot, it's going to be traveling down at a velocity of v. So if I consider the flight of A, that's actually identical to B once B returns to that level from which it was thrown. So that last part of the flight of B is the same as the flight of A. We can also see this on the graph, okay? If we look at it here, we can see that at this point here, the two objects are traveling at the same speed. And what is that point? Well, that's the point where rock B actually has a displacement of 0. This positive area and this negative area should be the same, and I realize I didn't draw that perfectly, but that's the point when it returns to its initial starting position. And we can see that this line here and this line here end up having the exact same look to them, which means that they hit the ground traveling at the same speed. They're identical from here on. We could simply shift this line and put it right here, and it would match up perfectly. So let's think about how we're actually going to go through explaining this. So the first point that I would make is that both objects are accelerating down at the same rate, 9.8 meters per second squared. The second point that I would make is at this point here, which I'm going to actually label as T on my graph, at T, as shown on graph, B has the same velocity as the initial velocity of A. And then I would say that this point is the point when it returns to the location where it was thrown. And you can even mention that the area under the curve is going to be the same at that point. So we can say from that point on, it has the same initial velocity and acceleration as A, so it must hit the ground traveling at the same speed. And there you have your answer. Definitely want to think about making your first point, that's key, and then having a few logically ordered supporting points that lead you to that answer. So there you have it.